we are now going to move to the third presentation of this session, which is about specifying and verifying future conditions. So this is work by Yahui Song, Darius Fu, and Wei-Ngan, and Yahui is going to give the talk, so please.
Right. Thanks for the introduction. Thanks for coming to the talk. So today I'm going to present you our recent progress on specifying and verifying future conditions. And my name is Yahui. This is a collaboration with Darius and our PhD advisor, Prof. Wei-Ngan. So future condition was introduced 1 year ago. It was introduced for the purpose of bug detection and program repair. So specifically, the bugs we are catching are some general types of bugs like memory usage or resource leak, non-pointer dereference, or more general bug type called unchecked return values. So there's an example of how we write future conditions as a specification. So future condition, we write for certain APIs that you want to reason about. For example, for malloc function, it will allocate heap memories. So the pre-post condition says that the input value size should be positive, and there's two possibilities on the return value. Either is a non-pointer or a non-pointer. And for if the return value is not null, then we will trigger an event called malloc with the argument of the return pointer. And in the future, we can describe the constraints saying that when the return value is not null, then remember finally to free the return pointer. So as we can see, future condition provide a way to write user-defined specifications for the important APIs. And it can capture the constraints after the certain function call. And it combines arithmetic constraints and linear temporal logics. For example, globally, the operators like globally, finally, next, etc. It enables modular reasoning, which means that each function is only reasoned once, and when it's being called, that it can be replaced by its verified specification. With that, we can also have lightweight specification inference. As you can imagine, if we have a specification for malloc, that we can infer the specification for the functions which make use of malloc. However, there are three critical limitations that from the previous work that the solution for entailment checking is sort of inefficient. And since it focuses on bug finding over soundness, which means that they can drop paths and can do strengthening of the program state, it does not have a formal guarantee that there's no missed validations. And because of this focus, it handles loops via unrolling. So therefore, this limitation also motivates this work that for the rest of the talk, I will explain to you why these are limitations and what are our technical contributions. With that, there's an example showing here. This is a use after free bug recorded from the CWE website. It has 3 buffers and have a sequence of operations on those buffers. So it starts from mallocing for buffer 1 and 2 and free the second buffer. And at some point, we have a use after free bug here at line 7. The reason why it is a use after free is that the argument used in string copy as a destination of some content was freed earlier before it's being used. So we like to use future condition and the reasoning techniques to detect such bugs. For that purpose, we define the specification for malloc, free, and the string copy. I have already explained the definition of the specification for malloc. So there's another future condition here introduced for free statements, which says that for the input pointer, once we freed it, then globally do not make use of this pointer anymore. And then the post condition of string copy triggers an event which makes use of the first argument. So we can imagine the combination of the future condition of free, which triggers from line 5, and the events which emitted from line 7 would capture this bug for us. And then it made use of a reasoning rule when we have function calls. So this is the extended version of Hoare-style verification for function calls. So what when we have function call, we retrieve the specification for this function. And the difference is that earlier we only checked the precondition that the current state entails the precondition of the function call. But now we will need to check that the execution, the behavior after this function call actually satisfies the future condition of the current function. With that as a guideline, the reasoning looks as follows. So when we have the first malloc, we trigger we have the first proof obligation, which says that finally free the first buffer. And then the left-hand side is just the rest of the execution trace, including mallocing buffer 2 till the last statement of freeing the buffer 3. And indeed, the first entailment check should go through because we have a witness in the middle of the trace saying that the buffer 1 is indeed freed. So the first entailment check succeeds. And this process goes on till when we have the first free statements on the buffer 2, and it triggers a future condition that globally do not make use of this buffer 2. And then we find that for the rest of the trace, that the statement of string copy at line 7, this event violates the constraint we had that it actually made use of buffer 2 at this point. Therefore, we captured a bug by a failed entailment checking. Okay, before that, so this process looks somewhat inefficient. So informally, it looks a bit of a quadratic complexity with respect to the number of future conditions that we trigger along the way. Because, for example, the free statements at the last line had to be checked 5 times for this simple program. So we propose a new solution for reasoning about future conditions, which to guarantee that each line of the code or each event emitted from the code is only being analyzed once. So the solution is to embed the future condition constraint into the program state and propagate it along the way. So at the beginning, we start from a simple program state, which has existential quantifiers over the program variables, and have empty trace. Epsilon stands for empty trace. And then the future condition field is underscore star, which means it allows anything to happen in the future. But when we have the first malloc function, that the trace has been extended with 1 event, and also the future condition is being added with 1 constraint that finally we need to free this first buffer. And the process goes on, we extend the events, extending the future conditions with the conjunctions there. Till that, we observe that at line, we had a future condition here that finally freed the buffer 2. And when we actually free the buffer 2, this constraint has been resolved into underscore star, which means that we no longer need to look for the free for buffer 2 already. The obligation has been fulfilled. And it continues to add more future conditions into the state. Till the moment that when we had a string copy event emitted, that by subtracting the string copy event from the future condition constraint, it leads to a false. So the error message will says that subtracting this event from this future condition leads to the false. So this is very easy for us to know that which future condition has been violated and why. So as we can see, we have achieved a linear trace processing that each event is only being processed once, indeed. And this is achieved by embedding the future conditions into the program state and manipulate the states using trace conjunction and subtractions. For that, we have achieved the first goal, which is to have a more efficient entailment checking, which has the linear complexity by reasoning about the future conditions. Now we show that how are we going to handle loops. So this is a false negative example shown in the previous work, that we are recursively malloc 5 pieces of heap locations into the array, but we only free the head of the array. So this would be a memory leak because we have malloc from 0 to 5 location of the memories, but then we only free it once. However, this will not be detected from the earlier work because it unrolls the loop exactly once. So if you unroll it, we will see, the analyzer sees that there's only one piece of memory being allocated, and indeed it's being freed by the end. So there is no memory free. There's no memory leak. However, we would like to capture such bugs so that to remove the false negatives. So the solution is that we can now provide the specification for loops via predicates of bags of future conditions. So now we not only can, instead of saying at the certain location of the memory that we have this future condition, we can provide a bag of predicates which captures a bag of elements which share the similar future conditions. So for example, here, the predicate has two arguments, have an iterator I and has a bag. So this is, is a bag of contents that for each of the elements in the bag that we need to free it at some point. With this specification, when we reason about the main function, when we call the malloc n, this will instantiate the predicates with a concrete bound, which from 0 to 5. So the bag is concrete now with elements 0 to 5. And then when we free only one of it, the subtraction will give us a residue which says that predicates now, the future condition is only contained from 1 to 5, as in the first element is being freed, so we don't need to capture its future condition anymore. And also correspondingly adding the globally do not make use of the first elements of the array into the future condition. In that case, by the end of the program, we will have an error message here saying, because it's the end of the program, the empty trace will not satisfy the obligation, which to free the elements from 1 to 5. That's why that's how we capture this bug. And more importantly is the method, how are we going to verify while loops. So this is it's similar to the traditional Hoare logic verification rule for the loops, which we need to find the invariant which holds at the beginning of the loop, also holds by the end of the loop, and we can conclude the state with the invariant conjunct with the negation of the loop guard. The difference is that we have extended the program state from arithmetic constraint and traces with a future condition here. So when verifying this while loop, we will need to find the invariant of this loop, which captures the predicates, which captures the behavior of the loop. So the syntax here is very similar to Daphne, that the invariant says that exists the iterator I, that for each iteration that so the predicate holds from the location 0 to I. And by running through the one iteration of the loop, we will be extending, when we have a more malloc here, we'll be extending the predicate first. And by the loop, we'll also increment the iterator, so that we'll also increment the value of I as well. By the end, we retrieve the same predicate with increased value I. So we say that the invariant holds by the end of the program. And we conclude that by the end, I is being greater or equal than n, and in this case, we can be more precise that I will be exactly equals to n. That's why we concluded this predicates by the end for the specification for malloc n. And the invariant is supposed to be provided by the users, and in this work, we provide very lightweight inference synthesis for such invariants as well. So now we indeed have a mechanism to write the recursive predicates for the loops which manipulate resources. Last piece, we're trying to have a soundness formalization for the proposed verification work, that it is sound defined as follows. So the soundness the formalization has been constructed by the following three parts. That the first one is we define an instrumented semantics for the target language, which says that is a big step semantics from a given program E, when it evaluates the concrete value V, it changed the concrete program state stack and execution trace to the primed version. We also define a semantics model for the trace specifications, as in what does it mean by saying that concrete stack a concrete stack and a concrete execution trace satisfy a given assertion with respect to the traces. And also we have a set of forward verification rules, which is the main contribution for this work, that which manipulate the future conditions and capture the violations along the way. So the soundness is defined, this is a definition of soundness in ROC, that it says if the verification system conclude a valid triple starting from a precondition, pre-trace, pre-future condition, and concludes a post-condition Q and a post-trace T2, theta2, and a concluded future condition. And then if the concrete state, stack state S1 satisfy the precondition and the execution trace at the beginning, row 1 satisfy the trace, the theta 1 at the beginning, and the big step semantics also transform the stack, transform the concrete state S1 row 1 F1 into S2 row 2 F3, and with a concrete value V here. In that case, it indicates the concluding value satisfy the post-condition Q, the concluding trace satisfy the concluded trace specification theta 2. And very interestingly is that the future condition concluded by the forward reasoning result has to entail the future condition concluded by the big step semantics. The interpretation of such an entailment is that it is only sound to strengthen the future conditions along the way so that we do not miss any violations. So I find it interesting because usually for verification works, we are allowed to over-approximate the program states, but in fact, it's only be sound if we only strengthen the future conditions along the way. Okay. So we have got a soundness definition for the verification work as well. So I'll briefly go through the experimental results. We have found a bunch of APIs in different scenarios. For example, for the file operation, open, close operations, thread usage, when we create it and you create a lock, you need to check the return value. Memory usage, socket usage, you need to close it. Database usage, and the general unchecked return value and non-pointed reference. So these APIs are found from the GitHub repository and as well as CWE websites, which captures all the common pattern of the bugs. We have done our experiments on around 1,600 plus lines of code. For that, we wrote 34 predefined specifications for the APIs. And then the tool can infer the specification for around 100 functions, which is the total number of the functions we taken in this experiment. It also inferred around 20 loop invariant, and the expected violations were 51, and we have reported 55 of them. So indeed, there is no missed violation, and they have false positives. And the false positives is allowed in the verification setting, but the cause of it would be the limited expressiveness and sometimes the weakening of the program states. There are case studies of those cases in the paper. You can check out more there. Right. So to summarize that, is to draw a comparison of what we have done in this work and the previous work is, so both of them are targeting at a compositional reasoning for temporal properties, and both of them employs lightweight specification inference. The difference is that the earlier work is focused on the under-approximation setting that you can drop paths whenever the path is getting too many. However, in this work, we can only over-approximate, so to weaken the program states when a path explosion happens. And obviously, there's a different treatment of the loops, one via unrolling, the other one via recursive predicates, but at the sacrifice that you need to provide the loop invariant. Since the earlier work doesn't need to write this invariance and can drop paths, of course, it's very suitable for large-scale usability. You can just run the analyzer, and whenever it's become too big, you drop paths. Whenever there's a loop, you unroll them. So it can target at a large-scale programs. However, in this work, we guarantee there's no false negatives because it is sound by design. And as I explained before, earlier work is also fast and mostly automated. But in this work, we try to improve the efficiency of the entailment checking. Okay, last point is that this work is more suitable for conservative analysis for critical systems, which you do not want any miss of violations. And both of them can share the future work that so far we have got no machine checkable certification. All the proofs are done by the automated tool. It's not machine checked. And it can enhance the expressiveness, as the first speaker in this session mentioned, that we can extend it to hyperproperty, but you need to think about how to deal with the trace subtraction for hyperproperties from there. With that, this is the end of my talk. Thank you for listening, and I'll be taking questions.
Okay, many thanks, Yahui, for the presentation. So we have a bit of time for questions. Yeah, please.
How do you relate this to separation logic?
Yes. Okay, the direct answer is that the trace abstraction is simpler than separation logic. And we indeed compare with, so technically the difference is that for separation logic, when they capture memory errors, it will run the tool, and by the end of the program to check whether the program state has residue heap allocation. In that case, they detect the memory leak, right? So we do similar things. We do for the same purpose, but use different ways using the trace representation and the linear temporal logic constraints to capture such violations. So the a more high-level difference is that this work is more targeting on the properties which can be represented as temporal constraints, and the memory violation is just one of it. For example, you can also describe things like this location of the memory has to be freed within 2 steps. Such things that this cannot be, these are temporal aspect, right? So it's very unique using temporal logic, which may necessarily can be achieved by separation logic. That would be right. Thank you very much.
Okay, maybe one more very quick question. So you mentioned you have formalized forward reasoning rules. Did you look into backwards reasoning? So it's very interesting here because what you have here is a trace abstraction, not a state abstraction. So would it make sense, or would it actually work for your set of predicates to try to look into backwards reasoning to have maybe something about necessary precondition or sufficient precondition? And to try to prove programs this way. Did you look into this approach?
That's a good question. I saw many mainstream tools are using backwards reasoning. I haven't thought about it. However, I think the main difference or the difficulty for me could be the how do we capture the loops when you do backwards reasoning, that to propagate a precondition, a necessary precondition to satisfy the post condition. This would so maybe there's difference there, but I don't need to worry about that now.
Thank you very much. Fair enough.
Thank you very
Okay,
much.
so thanks again for the presentation.